Hi sir, good morning one and all. Good morning sir. This is Sridhar. I am from Mechanical Engineering, second year, first sem. Today my topic is critical load behavior in columns with pinned supports. Critical load behavior in columns with pinned supports is my topic. Introduction to critical loads in columns. Critical loads refers to the maximum axial load a column can carry before buckling occurs. Understanding this behavior is essential for safe structural design. Columns with pinned supports exhibit specific buckling characteristics that need to detailed analysis. Definition of pinned supports. Pinned supports allow rotation but prevent translation at the ends of a column. They are idealized boundary conditions used in theoretical buckling analysis. Pinned supports influence the buckling load by allowing movement that affects stability. One beam is fixed, pinned is the fixed end. One end is fixed, other end is free end. One end is fixed end, another is pinned end. These are the pinned supports. Types of bucklings in columns. Buckling is a sudden lateral deformation due to compressive loads. Primary types includes Euler buckling and local buckling. The focus is primarily on Euler buckling on pinned columns. Equilibrium of the bulked column, deformation, extending and compressive loads. Euler's buckling theory. Euler's formula calculates the critical loads for long, slender columns with pinned ends. Critical load formula: P suffix Cr is equal to pi square Ei by L suffix whole square. Sigma suffix Cr is equal to pi square E into by L suffix C by R whole square. L suffix C is equal to KL. The formula considers the column's length, moment of inertia and modulus of elasticity. It provides a basis of understanding stability limits in idealized conditions. Assumptions in Euler's theory. The column is perfectly straight, homogeneous and elastic. The load is perfectly axial and gradually applied without dynamic effects. Boundary conditions are idealized as pinned at both ends with no movement resistance. Mathematical expressions of Euler's critical load. The critical load P suffix Cr is equal to Pi and Ei and KL, where E is the Young modulus, I is the second moment of area, L is the length, K is the effective length of factor. For pinned columns, K is equal to 1, simplifying the formula. Effective length factor in pinned supports. Effective length factors K accounts for boundary conditions and end conditions. For pinned supports, K is equal to 1, indicating the actual length of the column is used. Critical loads effective length and effective length factors for ideal columns. Change in supports to conditions after alter K and thus the buckling load. Influence of column slenderness ratio. The slenderness ratio factorial by length over radius of gradation affects buckling behavior. Higher slenderness ratio lead to lower critical loads and increased buckling risk. Design must balance slenderness to optimize length and stability. Critical loads, effective lengths and effective length factors of the ideal columns. Short versus long columns. Short columns tend to fail by crushing rather than buckling. Long columns are more susceptible to buckling at lower ends. Pinwood supports influence this transition by defining boundary conditions. Critical load P suffix CR is pi square E by L E suffix whole square. Effect of imperfections of buckling. Real world imperfections such as initial crookedness reduce the actual buckling load. Theoretical critical loads provide an upper bound often higher than actual capacity. Engineering must consider imperfections in safety assessments. Post-buckling behavior. After buckling, columns can undergo large deformation with minimal load increases. Pinwood supports may allow rotation, affecting post-buckling stability. Design for ductility and stability in the post-buckling range is essential. These are the Pinwood supports. One end is fixed, another is free. If the deformation is slow. Experimental is theoretical critical loads. Experimental tests often show lower buckling loads than theoretical predictions. Variability in material properties and imperfections account for discrepancies. Calibration of theoretical models with experimental data improves safety margins. Theoretical critical loads in equilibrium of the blocked columns conditions. Numerical methods for critical loads analysis. Finite element analysis provides detailed insights into buckling behavior. Numerical models incorporate imperfections and complex boundary conditions. Such methods are vital for verifying analytical predictions in real structures. These are also critical loads pi square EI by LE suffix whole square. Design codes and standards. Codes like Euro Codes 3 and AISC specify guidelines for buckling design. They incorporate safety factors and account for imperfections. Complements ensure success with Pinwood supports meet safety and performance criteria. Practical considerations in Pinwood columns. Real supports are rarely perfectly pinned. Some movement resistance exists. Connection detailing influences boundary conditions and buckling behavior. Engineers must evaluate actual boundary conditions for accurate critical loads estimations. Impact of material properties. Material stiffness and strength directly influence buckling capacity. Variations in material quality can reduce effective critical loads. Selecting high quality materials enhance overall stability. Case studies and applications of critical loads. Tall communication towers often employ Pinwood supports columns and require buckling analysis. Building columns with Pinwood supports are designed considering critical load to prevent failure. Historical failures highlight the importance of accurate buckling assessments. Innovations in buckling prevention. Use of bracing and stiffness can increase critical load capacity. Advanced materials and composites structures improves buckling resistance. Ongoing research aims to refine models for better predictions of critical loads. Summary of key points. Critical loads in Pinwood columns is primarily governed by Euler's buckling theory. Boundary conditions, imperfections and material properties significantly influence stability. Proper analysis and design ensure safe and economical column performance. Conclusion and future directions. Continued development of experimental and computational methods will enhance understanding. Incorporating real-world imperfections leads to more reliable designs. Future research aims to optimize Pinwood support systems for better better structural resilience. Okay, thank you, sir.